Welcome to the last day of FinTech DevCon. My name is Maria. I'm the engineering manager for infrastructure team at Alloy. My background is in software engineering. I've been in a variety of software engineering roles before moving into the infrastructure. And Meg asked me to add one joke to my presentation because my slides were very boring, so I added a very non-funny fun fact about myself, which was that when I was in university, I thought I would never need networking, so I paid no attention whatsoever to the class, and then now I'm in infrastructure, so I guess karma found me and punished me for that.
Awesome, and I'm Meg. I'm one of the senior cloud security engineers also at Alloy. Our team works very closely with Maria's to ensure that the infrastructure we deploy is holistically secure across all our different environments and across the entire life cycle of creating infrastructure. Previous to working at Alloy, I worked at Marcus by Goldman Sachs in both security and software engineering roles. And we're both joining you today from Alloy. And Alloy solves the identity risk problem for companies that offer financial products. Over 600 banks, credit unions, and fintechs turn to Alloy's end-to-end identity risk management platform to take control of fraud, credit, and compliance risks and grow with confidence. Founded in 2015, Alloy is powering the delivery of great financial products to more customers around the world. And so after you heard our intros, you might have put two and two together. Clearly, Maria and I both come from cloud infrastructure backgrounds. So obviously today we're going to be discussing cloud infrastructure with you. But we're not going to be talking about the differences in various types of compute services, the incredibly obscure database you've never heard of, but we're completely convinced will change the world, or why you should use serverless over containers and the cost benefits of each. Instead, our focus today will be about scaling your organization's engineering function by integrating the infrastructure deployment responsibilities into your application teams. Especially once your organization has really started picking up speed, you're growing your engineering function, you start making those strategic technology and infrastructure decisions, which you hope are effective now and in the long term. Later, though, the concern turns into how can your fintech maintain the velocity that you've started without sacrificing, one, the quality of product, or the ability to iterate and respond to changing market conditions. And our question for you today is how can you leverage your engineering organizations to empower each other towards this goal? Maria and I believe that integrating application engineers into the infrastructure deployment process will facilitate reduced time to market for your organization, increase the capability of your engineers, and enable cleaner compliance and security attestations. But maybe you don't believe us, so we will spend the first bit of our talk trying to convince you that we're right, and there are benefits to having your developers even touch infrastructure at all. Next, we will cover various team working models and how you can think about organizing your teams. We will end with our personal learnings in moving to this model at Alloy, along with the tools, processes, vendors that have assisted us personally. And of course, we'll leave plenty of time for you all to ask questions at the end. Now to our first point, which is convincing you all that having your application engineers touch infrastructure won't completely destroy your organization.
Why should software developers even touch infrastructure? We still see a model where software engineering teams are completely separate from infrastructure teams, also known as throw your code over the wall. The interaction goes like this. Application team needs a new service or the application. They go to the infrastructure team, and by some magic sparkle dust, infrastructure teams comes with voodoo infrastructure that's supposed to be perfect. There are some benefits to this approach. Infrastructure team can really stick to whatever standards they want, so there is some consistency in that. But are there any disadvantages to this model? Have any of you previously been part of this model, and have you seen any problems with this? Yes, we've seen lots of problems with this approach. So it's not always rainbow and sunshine in infrastructure land, and having teams completely isolated from each other leads to a variety of problems. What if the infrastructure teams made assumptions about compute or memory needed for the application to run, or what if they made assumptions about the scale that the application will be used at, and what if those assumptions are incorrect? The problems we're seeing is when something goes wrong, there is no clarity on who is responsible for what. Is software engineering team supposed to be responding to the incident, or is infrastructure supposed to be responding to incident? The siloed approach leads to disconnect between the teams. So we start seeing problems like slow feedback cycles. Application teams need to work on their personal laptops while they're waiting for the infrastructure team to complete their work. Software engineers are limited by resource constraints on the infrastructure side because the split is not always ideal. There are always more software engineering teams than infrastructure teams, and infrastructure teams can become a bottleneck. Disconnect and siloed knowledge can lead to resource inefficiencies in the world where metrics and availability monitoring created by infrastructure team, but application developers need to triage and fix problems in production. It can just become a rabbit chase to pin down the actual issues because they're not working together. Resource inefficiencies can directly cause financial inefficiencies because the teams that are responsible for reliability of the application are not familiar with the application itself. So response to every read message in Slack or every alert becomes just additional compute or memory until line becomes green again. Instead of actually looking for a real problem, maybe the bottleneck is the query that can be optimized. So when teams are not working together, they're not able to find the actual problem. DevOps movement came around 2007, 2008, and it was supposed to fix all of these problems. But what had actually happened? Why do we see a lot of DevOps teams failing? The problem is some of the DevOps teams were just rebranded operation teams or infrastructure teams, so nothing really has changed. In some other companies, we've seen that DevOps teams have actually hired engineers with application knowledge and infrastructure knowledge. But DevOps always leaned more towards the infrastructure side, and there's always too much work for them to do. If they're the only ones responsible for tooling for the engineers, for CI/CD pipelines, for availability, and for being on call for the application, there's just never enough time for them to do it all. So we see high levels of burnouts in those teams and sometimes inability to comply with security standards and slow time to market. As a result, frustrated teams started taking ownership of their infrastructure, which leads us to the next working pattern where application teams own completely all of their infrastructure, aka YOLO land. There are really good positives in this approach. There is no application team that is responsible for the infrastructure, owns the full life cycle of the application. There is no slowdown. There is no upfront dependency. They don't need to wait for anyone to create infrastructure for them. They are very familiar with all of the infra, so we can see speed improvements when team members are familiar with their stack. This model makes sense for companies in their early stages because you might not have capacity to have dedicated infrastructure folks, but you still need to have infrastructure to run your apps on. That has been the case with Alloy in their earliest stages. Teams were responsible for whatever infrastructure they needed to build to get application out the door. However, nobody anticipated the level of effort it will take later to migrate all the various patterns of the infrastructure into the cohesive standards. Even today, 3 years after the infrastructure team was formally created at Alloy, we still sometimes see little remnants of ad hoc infrastructure throughout various ETL pipelines. This sort of model can work well when application teams are distinct and completely isolated from each other, but it starts breaking down when we see that new teams are created or engineers are being moved from team to team. In the new formed teams, what standards do we adhere to now if there were completely different standards in two teams before? How do we help our engineers ramp up faster now because they might be familiar with completely different infrastructure stacks? What if we need to integrate two systems together and they live in completely different infrastructure worlds? The cost of infrastructure can also increase because different teams will be building solutions to very similar or same problems. They could also be using SaaS applications or providers to solve exact same problems, so company ends up paying more money. And implementing security best practices becomes difficult because security team now gets to get familiar with all of the different flavors of infrastructure.
The contrasting model, and one that we actively are following today at Alloy, is one where we do have our specialized infrastructure team, but the responsibility of creating infrastructure for applications is shared across numerous engineering teams. We do recognize it would be foolish to believe your company could grow indefinitely without having folks who have specialized infrastructure skills. But what we're trying to convince you today is that even once you have those engineers, the entirety of the swaths of infrastructure that your applications and your platform runs on do not need to rest solely on these team members' backs. At Alloy, again, we do have a dedicated infrastructure team, but we involve our software engineers in the ongoing deployment, iteration, and maintenance of infrastructure which is specific to their team's applications. This is accomplished by having our engineering team that's focused on building infrastructure into repeatable modules, which can be deployed on, iterated, and repeated by the software engineering teams. Using this pattern, we've been able to enable our limited infrastructure and security team to support 13 different production environments, a few dozen database clusters, and a pretty meaty software engineering organization. Compared to either the patterns where you have infrastructure YOLO land or throw your code over the wall pattern, some of the benefits we've seen of this are, again, more efficient development and reduced upfront waiting times for initial infrastructure provisioning. And that's because the infrastructure and the application itself can be deployed and built concurrently with each other. Easier integrations between systems, and also simpler enforcement and attestation of those infrastructure-related security and compliance controls, both due to the standardization that comes from the modules. And additionally, our on-call software engineers and infrastructure engineers all have more clarity to debug issues because they are familiar with the entire stack the application runs on. However, we do recognize that no pattern, theoretical or technical, is without its drawbacks, and choosing to follow this pattern necessitates the following within your organization. One, there will always be a learning curve in getting your software engineers or any engineers familiar with new tooling and practices, regardless of the tools, vendors, or specifics which you choose to implement at your organization. If you do not have the ability to dedicate the time or the temporary productivity decreases to accommodate that, we need to be aware of that when you're considering this model. Later, Marie and I will go into the specifics of the tooling and practices that we use at Alloy in order to reduce that sort of learning curve, but we haven't seen a situation where it's fully mitigated, so we just want to be upfront about that. Additionally, these patterns directly inject your infrastructure and your security teams into the work streams of application-centric initiatives. Your teams are no longer isolating and siloed
like little infrastructure land. So all of your teams need to be capable of this added collaboration. And that's also why you all as leaders within your organization need to be aware that this isn't solely a technical problem, that there are cultural shifts that need to happen within your organization that would make this successful. Because moving to this model is essentially an exercise in delegating control and responsibilities, which would have previously been carried out by your infrastructure and security teams. There needs to be very open and frequent communication and collaboration between, again, the security, infrastructure, and software teams. We see at larger organizations, the security teams in particular have a tendency to act as what we call security consultants, i.e. maybe popping in to technical discussions to give their very specific security-centric requirements of your solution, and then immediately leaving the chat before addressing any technical questions or discussing realistic implications of actually implementing these security controls into the solution. However, this manner will not be successful here. While teams are learning to do infra, and we've kind of injected these teams together, there needs to be active hand-holding and active teamwork. Additionally, there needs to be a strong understanding of shared ownership. When the job functions blur, so do the individual team's responsibilities. What would have previously squarely been, oh, that's an infrastructure problem, or oh, that's a security problem, is now mixed into multiple teams' domains. Blameless culture and a willingness to take ownership need to be in place so incidents don't become a nose-goes situation. In order to ease the burden, though, of moving to this distributed infrastructure deployment model, there are several tools and frameworks that can make this move easier, starting with infrastructure as code.
All right. What is infrastructure as code? Infrastructure as code is a practice where infrastructure is managed and provisioned with code or developer software development techniques rather than manual process. Utilizing infrastructure as code can be as simple as copy-paste, and coincidentally, this pattern can also lead to consistency in your infrastructure deployments. Our older infrastructure was not using infrastructure as code. So you can imagine what happened when, let's say, engineer went to remove permissions from the Lambda that was being decommissioned. They did not realize that Lambda was, that those same permissions were used in other Lambdas, so it led to the minor outage. Have you ever been in a situation where you did not have clarity on how certain infrastructure have been set up or what exactly it does? It becomes really disempowering to the whole organization when you're not using infrastructure as code, you're not allowing your teams to iterate. So now let's talk a little bit about what infrastructure as code to choose. An early attempt at Alloy to implement infrastructure as code, we went with CloudFormation and CDK. It was an obvious choice at the moment because we were completely AWS shop, and our software engineers got really excited because they could use languages familiar to them to create their infrastructure. However, as our scale grew, it became a little bit difficult to manage because CloudFormation uses more of an imperative approach to create infrastructure. It requires you to be very explicit about exactly how infrastructure needs to be created and about all of the dependencies between different resources. It also did not allow us to completely automate throughout the whole process. So we could not use it for tools like CloudFront or Datadog monitoring. So it sort of created a split in responsibilities when application teams could create all of their AWS infrastructure, but then they needed to create tickets for infrastructure team to add those additional things that are outside of the AWS ecosystem. Additionally, having to maintain configuration in multiple places restricted our ability to reach the end goal, which was completely integrated system. Similarly, community support and popularity of those tools are a little bit more limited comparing to the cloud-agnostic tools like Terraform. So let's talk a little bit about our challenges that we've had with Terraform. When we started using Terraform at Alloy in the very beginning, we used the monorepo model. In the monorepo model, you can see that purple circles are representing the modules. What are the modules? Modules are just collections of resources and configurations in Terraform. They allow you to group resources together logically, so things like, let's say S3 here, would contain S3 bucket with all the other resources related to it, like lifecycle policies or access control lists. The projects, on the other hand, are light blue circles, and they can be thought of as just your different applications or parts of your application. Let's say application 3 is your front end, and application 2 is just the back end of your service. So the problem with this approach is that every time you update the module, all of the projects that are using the modules get updated at the same time. Now let me step back a little bit and give you a little insight into the environment that we are running in. We are using cell-based architecture at Alloy, and currently we have 15 different cells, which is basically 15 independent replicas of the system. So with that said, some of these cells are dedicated to non-production environments. Some of them are regional environments based on geolocation. Some of them are made for disaster recovery, some for load testing. So there's quite a lot there. And in this way, every time we would update the module, as soon as code gets merged to main, every of your environments, every of your cells will get the same update at the same time. But what if we want to do more of a phased rollout? What if we want to only make a change in non-prod environments or in the load testing environment before pushing it out to all of the productions? So this kind of organically led us to the second pattern where we moved our modules from the monorepo into the multi-repo. In this approach, every module will have its own dedicated GitHub repository, and it can be released individually using semantic versioning. And then your project would just explicitly point to a certain version of the module. This will allow us to iterate. Very quickly, and it enables us to do phased rollouts. It helps us assert continuously that we're compliant and secure, as well as enable our businesses to move faster. When we started using version modules in this is how our team drew the line between engineering, security, and infrastructure team responsibilities when it comes to the modules. Responsibility of the infrastructure team is building the reusable modules with SRE principles built into the modules. Terraform allows us to include resources like CloudWatch or Datadog monitors and alarms right into the module. So when your infrastructure services are getting created, they have all the layers of observability built in right away by default. We also incorporate auto-scaling best practices in our modules and make scaling easily configurable and transparent for software engineering teams. We continuously patch, upgrade our existing, and improve our existing infrastructure, as well as enable disaster recovery, monitor cost, and constantly lead various cost optimization initiatives. We work closely with software engineering teams, support their new feature development or attempts to improve existing features. We review changes to the infrastructure modules that they make or the projects, provide all necessary tooling, and enable effective and collaborative process for them.
Similar to how the infrastructure team builds in those monitoring and alerting mechanisms into the modules of the resources, the security team is also implementing the security best practices into the modules and bootstrapping the infrastructure that is required for our security systems. We do this because, going back to our original problem, we aren't going to see much benefit if our application teams can deploy the infrastructure, the compute, the databases, right, that they need to run their applications on, but then they have to wait for the security team to sign off or wire in the security controls before they can actually start using this infrastructure. Because that is just effectively moving the bottlenecking team from the throw your code over the wall pattern from the infrastructure team now onto the security team. In addition, what we also do is we put those resources in line that enable our own initiatives. So as an example, a lot of our applications at Alloy use a database. Really crazy stuff here. So while the infrastructure team, makes sure the connectivity is there, our team is responsible for making sure the encryption, right, either at rest and in transit, the permissioning is locked down, etc. But what we are also responsible for is bootstrapping our production databases with the resources required by our temporary privileged access management, or TPAM system. Basically, in short, how this works is, we have a database and then we have another resource that sits right next to the database, which facilitates just-in-time access to the database for on-call production outages, that sort of emergency situation. And we do this because, one, we don't want to have any time, even if it's short, where the database is created, but we don't have that TPAM system there, right? So in that case, the database goes down, we're kind of sitting ducks in the water. We can't access the database for production, outage situations. And also when we are putting those resources directly in line with the database creation itself, we can ensure that not only is the database created in a same and consistent manner, but also that these resources that we use for our security systems are also always functional because they are likewise created consistently. Additionally, as an independent function, we build and maintain infrastructure related to our own team initiatives, so things like firewall, antivirus, really exciting stuff. As much as we'd like to say it's possible to completely get the application teams to make us not need to have a job and they can just do all of the infrastructure completely on their own, unfortunately, we are not there yet personally. So for now, we do all of the things related to security initiatives. And lastly, we have product engineering. At the forefront of our module creation, those teams are responsible for working primarily with the infrastructure and security teams to make sure that the modules that their applications need have everything in them, etc. And the application team is also responsible for the application's interaction with the infrastructure. So when we are thinking about that in AWS terms, it's importing those libraries for AWS cloud provider and the methods that will integrate with writing, reading files to S3, the database, etc. In terms of ongoing work, the product engineers use the modules then that have been created to deploy the infrastructure and to augment their infrastructure as their product requires new features. So some of the things we often see in terms of augmentation are adding permissions to their applications, adding new data stores, so things like S3, or adding connections to new database clusters, and provisioning additional AWS services such as Lambda for async processing, etc. So with the various teams managing different parts of the infrastructure deployment process, you'll be right to ask yourselves, how does this change impact our ability to prove compliance or security controls? As you all are probably really familiar, being in the fintech space means one thing and one thing only, and that's that you have to answer a lot of compliance questionnaires. So personally, very aware that this is a problem, and I hate doing it too. So when we think about how are we going to answer those questions when we, have many different individuals deploying our infrastructure, this is how we are thinking about implementing and building those guardrails around the deployment process. So first of all, our philosophy to implement these security controls is twofold. One, we want to make sure we're always following our standards, pretty simple. And two, we want this to be as easy as possible for us. So in our context, that means we want our control enforcement to be centrally managed to reduce basically the amount of work and systems that our security teams need to look at to assert compliance and gather evidence. So with our deployment process, this is a little bit of a high level how it works. Engineers make code changes on their laptop, push them up to GitHub, and then we use various tooling within GitHub to package up the infrastructure, deploy it, it gets created in AWS. So those are kind of the three places that, as an overall, we think we can inject security controls. And what we have is actually not just three different places you can inject different controls, but you can actually put your security controls in a few of these various places. So for example, linting and formatting, not a security control, but a best practice. You can either implement them as a pre-commit hook locally on the engineer's laptop, or do a check in your VCS system, i.e. if the code is trying to get merged into main and it fails this check, do not pass it, block the merge. So how do you choose where to put these controls? For us, we view non-critical controls, so things like code formatting, documentation, linting, etc. We implement them as pre-commit hooks on the engineer's laptop. And so basically, if you're not familiar, pre-commit hooks are checks that run right when you're actually committing code from your local machine that verifies the code meets whatever standards that the check is going against. And good pre-commit hooks update the code that failed so subsequent attempts are successful. These obviously run locally on the engineer's laptop. So there is a quicker feedback loop of problem to solution, and therefore less money spent on either running it in GitHub Action Runners or Circle CI or however you're building or storing your code. However, the limitation with pre-commit hooks is probably kind of obvious. Well, one, there's not consistency within your local environments. So these sorts of checks rely on the permissions, environment variables, and configurations of the laptop. And pre-commit hooks specifically are a bypassable control. They are quite easy to get around. You just say pre-commit, uninstall, and bada bing, bada boom, you are in the green. So for us, when we think about security controls, pre-commit hooks is not where we put them. So how we run our security controls is when we're looking primarily at that second stage. For us, that's in GitHub. So how we validate at Alloy our IAC against security misconfigurations is we use Lacework as a paid vendor. However, another great option for open source is Terrascan. The last place you could consider putting your IAC checks is what we have conveniently visualized as a box, but we're going to call almost like the infrastructure runtime. So that would be the place you could implement security controls almost as a just-in-time measure. For example, Kubernetes admissions controllers, if you're familiar, could fall into this category. You can think of these sorts of validations, again, as just-in-time, which is basically as you're creating Kubernetes resources, they are validated, they are compliant. Although we do utilize runtime controls for other security systems, we do not use them to validate or assert compliance on our IAC deployment pipeline for a few reasons. One, we want to be preemptive in preventing misconfigured IAC. When you're using things that operate basically post-deployment or at runtime, there is going to be a level of time, right, where it's either in the process of being provisioned or is fully provisioned before it can be determined if it's compliant or not. And we don't really want to deal with that. So that's like a negative for us. Secondly, they aren't necessary in our case. There are definitely reasons why people would choose runtime-based checks for IAC or infrastructure provisioning, and that's often when you might have multiple VCS systems or people are deploying deploying their infrastructure from various locations. For us, because we are using a centralized system in our GitHub repositories, we don't need to, distribute the checks at runtime. And also, we find that using these sorts of runtime checks for infrastructure compliance makes people's lives harder. For example, engineers might see their IAC pass the build and was deployed, but the security, the changes aren't reflected, right? Because at runtime, it was determined this is non-compliant, I'm gonna kill it. What gives? You would have to dig then into the runtime of the logs of whatever system is doing the runtime checks. That's a whole different system you have to look at. And additionally, on my team's responsibility, that actually complicates our security attestation, because now what we're seeing is, again, differences between what's in main and what is actually the live infrastructure. And I don't want to be looking at multiple systems to determine if we're compliant or not. So in short, there are several places you can put IAC scanning controls. We personally lean very heavily on VCS-based implementations, with the awareness of where we implement these controls directly impacts both our team's experience and the team experience of our software engineers as well.
Similar to how security team enables our engineering to move faster, our infrastructure team is also focused on how we can get our systems and tooling to support a decentralized infrastructure working pattern. When we started with Terraform, we used local applies from local computers, but the problem with that is individuals need elevated access to AWS. It also does not support or prevent simultaneous changes, so it can lead to completely unpredictable outcomes. Therefore, we introduced Atlantis. What is Atlantis and why Atlantis? Atlantis is basically an open source tool that works like a GitHub bot, and it allows you to manage Terraform commands in your GitHub. So the pipeline with Atlantis will look like any engineer with GitHub access can open a pull request with their Terraform change. They get it approved by security or infrastructure team member. And then in order to deploy changes, all they need to do is just comment on the pull request, hey, Atlantis, apply my changes. So after that changes are getting deployed, and post-deploy, they will get merged only if deployment was successful. So it works really well. And we chose it for a variety of reasons. One is being an open source tool, good community support for the tool. It does not cost much, especially comparing to tools like Terraform Cloud or Terraform Enterprise that could cost a fortune and nickel and dime you for every single run of your infrastructure. The other thing we do is we try to hide some of our complexity by separating modules with application-centered focused from modules with infrastructure-centered focused. So the infrastructure-centered point of view will include modules that are related to networking resources that are needed for applications to run, or the runtime resources like EKS. And usually our team and security team are primary owners and mostly responsible and working on those modules. And then we have all the application-centered modules that will include resources needed for the application to satisfy whatever business requirements they have. So they will include things like S3 bucket that has front-end assets for a particular front-end, or it'll be the IAM permission, IAM role that's needed for the application to run. Having both of these decluttered from each other helps the application-centered helps us declutter application-centered infrastructure from underlying shared runtime environment that it runs on, so software engineers can focus on what matters to them for their application. We also utilize pre-commit hooks in order to update Terraform providers. In this way, we really remove the need for software engineers to know like all the different nuances of the Terraform providers, and they don't need to worry about that. They'll get the latest update when they're pushing whatever change they're making. Lastly, things like Dependabot can help automate the version upgrades of your modules across the projects. So especially it gets useful when you get over 3 Terraform dependencies and you start seeing issues where your modules fall behind on the patches to issues. By automating process of updating dependencies, we can significantly save developers time, improve consistency, security, and maintainability of your projects. Now let's talk about what else can be done beyond what we've discussed. We are looking to implement some of the testing for our Terraform modules. Continuous testing is important because it can help you have confidence that whenever you're making changes to the modules, you are not breaking the order of operations in the projects where modules are being used, and you are not introducing circular dependencies. So testing can be done with tools like, there's a large number of different tools, and you can use things like TerraTest, or Terraform now has native Terraform tests that can be used in order to test your Terraform modules and projects. The other thing we're looking at is the cost savings and how we can improve that process. When your software engineers are empowered to deploy whatever they want, they're not always driven by the cost savings initiatives. So that sometimes leads to problems with occasional cost spikes where resources are misconfigured or over-provisioned. A few weeks ago, our engineering team launched the S3 bucket, utilizing non-optimized encryption configuration for the S3 buckets with the frequent access patterns, which led to $20,000 bill, I think, in one weekend. And we did not notice the issue during the pull request review. Like, we're all human, we can miss things when we're reviewing PRs manually. So what happened is, after the weekend, we received the billing alert on Monday, like, hey, you crossed your threshold. But let's be honest, billing alerts can be really difficult to configure, and they can be difficult to maintain because you always have to change them to accommodate the growing business needs and initiatives that are happening. So you always have to keep revisiting them and changing. Therefore, introducing preventative cost analysis tools like in your infrastructure as code pipelines, like InfraCost, for example, can really help you to detect these potentially costly changes before they even get into your production, before they even get deployed. Another problem we're looking to solve is the drift detection. Imagine a scenario where engineer goes maybe during on-call, maybe there is something he's testing, he goes and changes the size of the EC2 instance. That can lead to, without updating the Terraform code, he goes right into the AWS console. This manual change could lead to increased cost and potential performance issues if not properly accounted for. So regular drift detection is a good practice that can help you address code deviations. The deviations can come, as I mentioned, from things like incident response or maybe some hiccups in your release pipelines. Drift detection will allow your teams to, revert change, and if the process works properly, teams will know that they need to address the change. They will either revert it or they will, accommodate the code accordingly to accommodate for the change. Knowing that the actual infrastructure matches what's in the Terraform state and in your code mainline simplifies troubleshooting and debugging, and there is no ambiguity about the consistent setup that you have.
And so with that, we just wanted to end with a little bit of a conclusion, which is there are multiple ways you can integrate your infrastructure and software engineering teams throughout the infrastructure lifecycle. And we hope that you've learned maybe that embracing this pattern can help balance your low deployment timelines with cost efficiency while maintaining security and the operational benefits of standardized cloud infrastructure. With that, we would like to thank the conference sponsors for making this possible. We would like to open for Q&A, but I recognize we are kind of tight on time, so if you would rather just pull us aside in the hallway, we are conveniently identifiable by wearing matching t-shirts. So with that, thank you.